Hey guys, and welcome back to another week in our first semester. This is week 2 of Module 1. And as you can see from our first equation up here, we're going to be doing some math today. So continuing with the trend of oxygen delivery and other interesting topics regarding that and CO2 transport, I'm going to get into some equations with regard to oxygen delivery, oxygen uptake and metabolism, and maybe some respiratory quotient things. So none of this should be necessarily groundbreaking and new for you guys, but not many people use equations after they've learned them, and this math really is helpful bedside if you know how to use it. If you're managing things such as ECMO, or you're in units that use a lot of monitoring devices, you can actually get a good picture and do some proactive care with these values. So I just like using things like this. The key to understand when you're using these calculations is to interpret them with a critical eye. You have to understand that the human body isn't static, so if you're confining something like the human body to an equation, you often might get misled, and you might make a decision that doesn't really make complete sense. So for example, we all know ABGs. You draw an ABG at one point in time, that doesn't necessarily represent every point in time. Anything could change that variable, so you always have to keep that in mind. But it's always good to have some sort of foundation of understanding. So that's what we're going to do with this today. So we're going to begin with the basics. We're going to start with the CaO2. We all have probably seen the CaO2. So it's a complete arterial oxygenation, and it's simply 1.34, which is the mLs of O2 that dissolve in 1 gram of hemoglobin. Actually, the more accurate number is 1.39, but we use 1.34 to compensate for different levels of met hemoglobin or carbon dioxide or anything that is dissolved in the blood naturally. We're going to go over to the SaO2. So we just throw that bad boy in there because that's how this is all calculated. This is how oxygen is transported, hemoglobin and how much it's saturated. Over here to the right is the how much PaO2 dissolves in the plasma, which is a very insignificant amount. So this is a coefficient we use to describe that. Oftentimes, you don't need to calculate this, especially in a test. It really is waste some time when you can really just focus on this first part of the equation. But anyway, just for lecture purposes, that's what that stands for. So the amount of oxygen that's dissolved in the plasma, that's the coefficient we use. So the normal value is approximately 20 ml per deciliter, right? Which is also referred to as volume percent. You will see it as such, so you know what that unit is. All right, there you go. Pretty straightforward as far as that goes. We'll talk about how to incorporate these things a little later. All right, so let's go to its sister calculation. We have our CVO2. So our CVO2 is essentially the same exact calculation, but instead of your SaO2, you're going to use your SVO2. All right, and then you can do plus because there is still oxygen dissolved. All right, and like I said, you don't have to use that if you don't want to. For our examination purposes, I'm going to give you some buffer as far as answers go, or a multiple choice, and you can kind of figure it out, whatever's the closest value. Okay, so no worries with that. All right, now that we have these two equations established, we're going to talk about our DO2. Okay, DO2 stands for delivery of oxygen. It's pretty straightforward. This is in mLs per minute. As far as units go, units are very important to know. And DO2 is your CaO2, right, times your cardiac output. And what is that? So that is let's make that a different color. That is 1.34 times your hemoglobin concentration times your SaO2, right? There, and then this is, that does not look like cardiac output. All right, and that is your cardiac output, which is your stroke volume multiplied by your heart rate. And we all know that. And I also forgot a factor of 10, and that is to convert the units into mLs per minute, okay? If you didn't use that, you wouldn't have the correct units to do any of these calculations, so it's very important you remember that. Because you remember this is expressed in mLs per deciliter, so that's kind of how we change that up. You just multiply it by 10, and then it gets rid of units, and so on and so forth. But just remember that, okay? I oftentimes forget to use that and just have to figure it out again, but all right. So normal DO2, so the delivery of oxygen is, let's see, let's pick a color here. So the normal DO2, let's get a color with oxygen. So normal values for this equal about 900 to 1100 mLs per minute, okay? You're going to see something very interesting with the DO2 and VO2 in a second, and it's going to explain a very important topic with oxygen consumption delivery. All right, so moving on with that, I'm building up on these equations to lead into our last one, so it's not kind of backtracking too much. Let's see, so this one we're going to talk about our oxygen extraction ratio. So with this being a ratio, obviously it's going to be a fraction. All right, so how we figured this out is we take our CaO2, all right, and then we subtract that from our CvO2, which makes sense, right? Two different systems, and one represents how much oxygen is there and how much oxygen we used, and then divide that again by our CaO2 as a percentage, okay? And you can multiply it by 100 if you want, but we're just going to leave it. So this is generally 0.2 to 0.3, right? And you'll see how this is represented in the difference between, for example, SaO2 and SvO2. Okay, that's neither here nor there, but think about it. Okay, we'll talk about that in a sec. All right, let me get rid of this. Okay. All right, so now that we have these four equations established, we're going to go to our VO2. Okay, VO2 stands for your volume of oxygen consumed. So you'll hear this as a measurement a lot of times for athletes. It's kind of a barometer for metabolic efficiency and things like that. So it's an interesting measurement, but in critical care, it's also a very interesting measurement because the balance of the VO2 and the DO2 really can represent significant issues in oxygen metabolism and kind of can give you a prognosis of different disease states and progression of disease states. So with that said, VO2 is a little longer. So we have our DO2. What do we do our DO2 in yellow? So we got our DO2. Ooh, let's make this bigger. Now let's make this all a different color. So our VO2, we're going to do it kind of like a, there we go. So VO2 equals DO2 times, and this will make sense to you, your O2ER, oxygen extraction ratio, right? So the amount of oxygen being delivered to the amount of oxygen being taken out as a percentage. So we'll break this down again really quickly. So your DO2, what does that equal? That equals your CaO2 times your cardiac output, okay? And then you're going to multiply that by your oxygen extraction ratio, which is CaO2 minus CvO2 divided by CaO2. All right, you still with me? I sure hope so. All right, so your normal VO2 is usually around, we have here 200 to 270 mLs per minute. All right, take a second to think about that. Look at the difference in these numbers. So let's say you have your VO2 of 200, you have VO2 270. Let's go with the low and high numbers. You have a DO2 of 900, and a DO2 of 1100. I'm sorry. So as you can see here, we deliver much more oxygen than we really need to take up, which is a very important process as far as reserve goes, okay? We're going to talk about a concept called critical DO2, which is where your VO2 is supply dependent. At this point, it really isn't. So let's see. So if you look at this ratio right here, so we're going to talk about some clinical parameters that are somewhat important. If you look at that ratio right there, the 900 to 200, right? That is almost a 4-to-1 ratio, no? All right. This ratio is a very important parameter and what we can use as far as adequate oxygen delivery. Oh, I got that mixed up. That'd be a bad ratio if that were the case. So you have your DO2 to VO2, okay? It's approximately, obviously that's not quite 4-to-1, but this is the value we generally use, and I'm just using this for illustrative purposes. So you want to deliver 4 times as much oxygen as you are consuming. And that's just how our normal metabolic process is as far as reserves go. But once we get less than that, we start getting into problems. So that's called our critical DO2. And Marino in your text actually does a very good job describing this, DO2. So that's basically when we're extracting 50%. Okay, so that was at 1-to-1. And that's our critical DO2. What happens is there's a nice graph in the Marino text, but it's kind of the reverse here. So the relationship you have your VO2. We're having technical difficulties today. VO2 and DO2, right? So clearly here we have an abundance as far as oxygen goes, and we kind of sip, right? We just sip from the blood, and depending on what we need, our metabolic needs or anything like that, we're working out. We take some more, but we never take too much to a point where we start dipping into our serious reserves. So let's say we have a point here, and we get about here, then we get a point here, and we get all the way to, all right, that's 0, 0. Okay, so this represents how our VO2 and DO2 interact. It's generally fairly buffered, as we've already established, so this will be our normal. Okay, we're going to be going this way. That way. All right, so that's our normal point. This is our max ratio, right? So this is about the point here, and then we'll go down here, and this is our critical DO2. All right. So right here is our 50% extraction. That's the magic number that we're looking for, where we're like, okay, we need to do something about that, all right? So if you look at it this way, if you think about an extraction ratio of, let's say you're on ECMO, or you have just another monitoring parameter, and you can actually measure someone's SaO2 and SVO2, okay? I use ECMO a lot because these are a lot of things I use while sitting pump, and it just makes my job easier, and I have everything I need to look at, so it's very convenient. So let's say your SaO2 is 100. And your SVO2 is 50. Bing, bang, boom. What do you got? You're at your critical DO2. And if you look at the clinical picture, if you're giving 100% or you're 100% saturated going to your patient and you're getting only 50% back, it's really easy to surmise that your O2 ER is very high. Okay? I think that's very straightforward. The whole point of this is to understand that when you're at that point, I mean, it's definitely purely supply and demand. You no longer have this 4-to-1 buffer. This value is somewhat useful. There's a lot of things that can mess with that, and that's why I prefer to use a ratio instead. For example, this extreme example right here. So a 4-to-1 ratio of DO2 to VO2 is a very good baseline parameter to really adjust your let's say your ECMO settings or FiO2 or blood transfusion or whatever it needs to be to supply this adequate oxygen in this face of this increased extraction ratio. So I hope this is somewhat clear as far as that goes, but you can see how all these calculations that we never use really come into play. You can't do one without the other, obviously, so that's kind of why I built that upon there. So let's just review really quickly on what was just said as far as these calculations. All right, so we went over our CaO2, right, which is the amount of oxygen that dissolves in 1 gram of hemoglobin and then your saturation of your hemoglobin, okay? It's pretty straightforward. You have 20 mLs per deciliter. CvO2, good thing we came back. CvO2 is normally, for your CvO2, about 15 mLs per deciliter, okay? So you have about a delta of 5 between that. 5 mLs per deciliter, okay? Your DO2 is your CaO2 minus, or times your CO2, which we just covered is your stroke volume times heart rate, times 10, okay? And 10 is to convert the units that you need to convert them into. The oxygen extraction ratio is simply your CaO2 minus your CvO2 divided by your CaO2, as you'll get a percentage. Like I said, if you want, you can multiply that by 100 and make it a nice pretty 20% or 30%, whatever you like. And those are the normal values as well, approximately. And anywhere else is plus or minus 5%. And then we have our VO2, which kind of builds upon a few of these other equations. So as you see with the DO2, you're using your CaO2 times your cardiac output. I know it looks like 10. Let me see if I can fix that. Okay, then you multiply that by your oxygen extraction ratio, which we already understand our CaO2, we understand our CvO2, and then we understand our CaO2. All right, and we established that our VO2 is approximately 200 to 270 mLs per minute in normal physiologic conditions. This can be increased in hypermetabolic states, fever, exercise, things like that. And you should see that in your readings, other pathologic states that really increase this. This is just supposed to be a highlight of your assignments. And then we talked about the DO2 to VO2 ratio, which we really want to shoot for, a 4-to-1 ratio, okay? We talked about our critical DO2, which is 50%. That's the point we begin to extract oxygen beyond our buffering capacity, so it becomes a supply and demand between the VO2 and the DO2, okay? So at that point, any fluctuations, severe fluctuations in your DO2 are going to decrease your VO2 significantly, and usually this remains constant, and that just keeps decreasing, and then we end up about here with no oxygen available to the body, and we go into anaerobic metabolism, and we all know the trend of that. So we illustrated here your SaO2 and SvO2, the difference, which would demonstrate an increased O2 extraction ratio. In this example, we demonstrated the 50% or the 50 mark. So just keep that in mind. The whole point of this is to understand these calculations and be able to apply them in a scenario, okay? So a scenario might look like, you have your patient on ECMO, they've become febrile, their white blood cell count has increased, they paint a picture of sepsis basically, and you'll be given these parameters, as you'll have their cardiac output, and you'll just go ahead and calculate these few things from there. So your O2 extraction ratio, what's their DO2 to VO2 ratio, and so on and so forth. Okay, it's fairly straightforward. It's not going to be too complicated, but it's very helpful to understand these different equations. So thanks for watching, and hopefully you guys can give me some feedback and send me some criticism, anything to make this better. Alrighty, thank you.